So, good evening, everyone. Let us continue our discussion and go for the seventh week lectures. The this week basically we will be discussing about sustainability. It will be basically on sustainability. So, what is sustainability? How it is important, and what are the design principles associated with sustainability? So, we will be going through all this in detail. Okay. So, let us start. So, design for sustainability. So what does sustainable design mean? So this means basically designing objects that are from this basically implies for designing objects that are from renewable sources, designing for need and function, designing objects that have a positive long term social impact, and understanding whole earth negative impacts that a product may have and turning them to positive basically. So that is whole idea of sustainable design. Why is sustainable design good? So because we live in an ever changing world, looking after our planet is important for the generations that will follow. Reducing our carbon waste helps promote the growth in our planet's ozone layer. Reducing our carbon emissions means that our planet is more likely to continue to exist in its current form. Changing our attitudes to what we buy and how we design can help, and using materials that are from resources that won't run out and will benefit the planet. So basically we have to develop our design ideas. Okay, so by this what is meant? So by developing our design ideas and finding ways to reduce the carbon footprint of our products, we can help our planet. Okay, and we can improve our designs in many ways. So there are some simple ways to develop our design ideas to reduce the product's impact on the environment. So they are basically, the most important concept is the 3R concept that we all know. It is very famous. Basically it is reduce, reuse, and recycle. Okay, so they are in this order. Firstly it should be reduce, secondly it should be reuse, and thirdly it should be recycle. So they are in this order because reduce is the most important part. Okay, you must reduce as much as you can. When you are designing as this will benefit the planet immediately, there are many things you can reduce, from the materials and components you use to the energy and time it takes to manufacture your product. Okay, so the most important component out of the 3R is the reduce. So uh, now let us see what is life cycle. So understand the life cycle of your product. Okay, how can you improve its life cycle and make it last stronger? So that is one of the important question for life cycle. So some of the ways can be: firstly, make it strong; secondly, use materials that will last; thirdly, choose the best joining methods you can for the materials that you have chosen; fourthly, try not to mix materials. If you have components in another material, find a way for them to be separated easily once the product becomes waste. And lastly, think seriously about what will happen to your product when it is at the end of its life cycle, and how to reduce its effect on the environment. So these are some of the ways how to care about the life cycle. So apart from that, there are material properties involved. Okay, so some of the important properties are the embodied energy. Okay, so this is basically the energy that any material uses, okay, when it is manufactured or made. For example, glass has a high embodied energy because it uses a lot of energy for its manufacturing. Similarly, wood has a low embodied energy. Okay, so it is the opposite of glass. Sorry. So because it uses less energy to be made, when using a material, think about where it has come from and how did it get to be in front of you. So this is the embodied energy basically. And so like we can say, like, we need to understand the material properties. What are the properties of the materials that we have chosen? Do they match the requirements of the product? So these are some important parameters. So based on that, we should develop our own design. Okay, so this is an example of sheets to show sustainable development of the product. So designs need to be developed to reduce their impact. We need to think about ways in which we can change and develop our design to make it better for the environment. Okay, so these are some of the ways, like, we need to note down and try to find out the sustainable development of our product. Okay, through brainstorming basically. So As we know, this famous definition of sustainability, as per the Brundtland report of 1987, so it is the development that meets the needs of the present without compromising the ability of future generations to meet their own needs. So this is the very famous definition of sustainability: meeting our own needs without compromising the needs of the future generations. Okay. So what is sustainability basically? So in industrial revolution, it released during industrial revolution, it released billions of pounds of toxic waste into air, water, and soil every year. It created materials that cause concern by that could cause concern for future generations to their quality of life. It produced large amounts of waste. It required endless regulations to simply regulate the rates of damage of points above. Okay, so that was the effects of industrial revolution. Okay, some of the ill effects. So if you see, like, traditionally, so during the industrial revolution, traditionally this was the economic model. Okay, so basically the economic part was the biggest. If you see the circles, so the bubbles, if you see, the economic bubble is the largest, followed by the environmental and social. Okay, so social was the last. And if you see, all of them are they are separated. There is no intersection, they are not connected. Okay, so all of them are separated, and first priority is the economic, followed by environment, and last is the social. That was the economic model during the industrial revolution. So it was understood that the sustainable system is basically cyclical. Okay, so for example, there is raw materials, out of that there is a product. Okay, say for example, in the tree ecosystem, so from the soil the plant is grown. Okay, the tree or plant is grown, so that is consumed by the animals. Okay, so for example, in this case, the squirrel is taking the plant, okay, the food of the plant, and based on that, it is throwing the waste, okay, waste into the soil itself, into the ground itself, and that is consumed by the small insects and rodents and various other small animals, like small organisms, which try to decompose that product. Okay, so this is the example of that. So it is consumed by them, and as a byproduct they produce again the raw materials. Okay, so it is basically the energy is cyclical. Okay, so basically the energy is transformed from one form to another, and that is what is all about that is what represents the sustainable system. It is basically cyclical. Okay, so from that only it was understood, like, from the industrial revolution model, okay, of economic model of industrial revolution, it was there was a green shift. Okay, so there was a green shift basically where like, instead of all the three bubbles having separate priorities and not connected, it was seen that more or less all of them had the same bubble in the green shift, and all of them were mostly, like, major intersection was there. Okay, mostly they were connected. Okay, so if you see here, the economic, social, and environmental all form a part of the big circle. Okay, large circle, and mostly they are interconnected. So that was the concept of the green shift. Okay, so how sustainability was introduced to people. So basically the the sustainability, the usage of sustainability, basically it started from 1992. Main emphasis started from 1992, precisely June 13th. Okay, when there was development of Agenda 21 at the World Summit. Okay, so at the World Summit of June 13, 1992, there was a development of Agenda 21. Okay, so in this summit, representatives from entire world, okay, so they actually basically represented 90% of the Earth's population. Okay, so they basically covered 90% of Earth's population. So they represented 90% of Earth's population in the summit, and it was found to be the single largest gathering of heads of state in history of international diplomacy. So such was the magnitude of this summit, that it was basically one of the single largest gathering of heads of state in history of international diplomacy. Such was the gravity of the summit, or the Agenda 21. Okay, so in Agenda 21 there were six basically categories. Okay, which had been discussed. One was the quality of life on earth. Second was the efficient use of the earth's materials. Third was the protection of our global commons. Fourth was the management of human settlements. Fifth was the chemicals and management of waste. And last was the sustainable economic growth. So these were the six category of agenda, which had to be discussed in Agenda 21, which were discussed in Agenda 21. So there, if you like from that, if you see, like for how do we get there from here. Okay, so that was basically discussed in that agenda 21. So it was found that initially, like in the primitive ages, the sustainability, if you see, so there was no net impact. Okay, because people had primitive habits. There was no like the modern use of modern gadgets and modern items was very rare. Okay, so they did not have the technology, so everything was very raw and primitive. Okay, so it was a primary form of use. So that's why there was no net impact on the climate. Okay, but after the industrial revolution and all the advancements in science and technology, so people started using various gadgets and equipments, machines, and that resulted in a lot of emission and various other toxic release into the environment. So that resulted in the large negative impact. Okay, so it like the decline of sustain like the decline of the gravity of impact increased year by year, decade by decade, and now it is currently in this point. Okay, so we are presently here, and it is like estimated, like because of the ongoing research. Okay, so the environmental impact will get reduced with with the future, within the future years, and a time will come when there will be no net impact. Okay, like the primitive times. And after that, okay, after that the emission will be completely stopped, and everything like will be good for the everything good for the environment will be done. Okay, so no emission, like everything will be absorbed and there will be no emission. So then it will result in a positive impact. Okay, so from large negative impact which is currently we are having, there a time will come in future due to the advancement of science and technology when there will be no net impact, and further advancement in technology will result basically in a positive impact when all the emissions have been either sorted out or they have devised various mechanisms which will basically convert the waste into wealth. Okay, so that will result in a positive impact. So, if you see, like the definition of traditional engineering, so what was it basically? So it was basically it required to solve problems that were presented with to the best of their knowledge, without constraints of within constraints of approval authorities and within schedule and financial constraints. Okay, so basically it did not have any environmental factor. Okay, so it needed to be like in traditional engineering, it required to solve problems they are represented with to the best of their knowledge within the constraints of approval authorities and within schedule and financial constraints. No environmental constraint was there. Okay, and engineers search for methods that maximize function and minimize cost to clients. So that is basically what is engineering is all about. Okay, maximizing the function or the output and minimizing the cost to clients. So output and product, and the this one, the finance, these were the main two terms. Okay, basically for the engineering community or the basically engineer. So they find out the best optimized ways to maximize the function or the output and minimize the cost to clients. So the maximizing utility while minimizing the cost to the client, that was the traditional engineering. And when there was a shift, okay, to shift in engineering mindset due to sustainability, so it resulted in like converting from maximizing utility to maximizing social benefit. Okay, and from minimizing the cost to the client, it was minimizing ecological impact. Okay, so in traditional engineering it was maximizing utility while minimizing the cost to the client, whereas in shifting like when due to advent of sustainable concepts, there was a shift in engineering mindset and it changed to maximize social benefit while minimizing ecological impact. Okay, so that was basically the change. But the issue is, how do we track this progress? Okay, so this progress has basically three parts. Okay, one is the social effect, where there is community activities, employment rates, immigration. One is the economic activities, where there is business growth, employment rates, inflation. And one is environmental effects, where there is beach closures, smog warnings, environmental contaminations, endangered wildlife. And apart from that, there is birth defects, death rates, severe asthma attacks, etc. So how do we sorry, so how do we track changes to these factors? So these are some of the factors which have a big role in judging the progress of the change in engineering mindset, basically sustainability. Okay, so these are the main three factors. So within this there are sub factors, so we need to track changes to all these factors. So how should it be done? Okay, so that is the basically problem or the question, okay, so that will address the sustainability idea. Okay, so designing towards sustainable development, so we should be aware of issues and impacts. Okay, inherently includes well-being of environment. We need to comply and go beyond minimum requirement, and we need to involve public and communities in decision making. We need to set our mindset to doing what is right, even when appears to be a more difficult process. It is a step in the right direction, and we must change the way people think about sustainability. So that is the important concept or important traits required for design towards sustainable development, or going forward towards sustainable development. Okay, so in that case, like, we need to step back from business as usual. We need to find ways to work with nature. We need to lessen environmental impact. We need to save energy resources. We need to build on small successes, piloting. We need to spread the word, market your capabilities to both existing and new clients. So the challenge goes beyond just the money. Okay, so there are a lot of challenges which we need to address, both mentally, physically, emotionally, and various in other ways. Okay, what professionals can do in this regard. Okay, so we need to design project to firstly reduce material and energy use. Secondly, we need to use renewable energy resources. Thirdly, we need to maximize lifespan of structure. Fourthly, we need to reduce construction waste generated. Fifthly, we need to reduce or eliminate hazardous waste generation. And sixth, we need to minimize maintenance and services required. Okay, so these are some of the ways we need to design the project. Okay, and most importantly, design project either reduce or eliminate greenhouse gas emission, use of ozone depleting substances, key air pollutants, and indoor air pollutants. So we need to either reduce or eliminate these four important factors. Okay, so this means that we need to consider all costs beyond just the dollars, including energy, water, sewage, chemical materials, maintenance and operation, lifespan, and replacement cost. Okay, so we need to consider all the costs. Okay, beyond just the income or the output or the what is the turnover we are making in terms of dollars. So we need to consider all the costs. Okay, so uh, like basically in sewage treatment plant, okay, in projects, so we need to use digester gas for energy. We need to use heat exchanger on sewage effluent. We need to use heat recirculation from transformers or blowers. And we need to use irrigation using plant effluent. Okay, so these are some of the ways. Okay, so how to uh, basically is perform sewage treatment, okay, in plants. So these are the ways we can look forward. And in case of urban development, okay, so we need to try to redevelop the brownfield sites. Okay, so what is brownfield? So it is an area of land that may have been contaminated by hazardous substances, pollutants, or petroleum, and which may be difficult to redevelop. Okay, so we need to find ways how we can redevelop those brownfield sites. Secondly, pervious pavement in parking lots. Okay, so pervious is permeable. Okay, so how we can make permeable pavement in parking lots, okay, so that water can percolate down. Okay, and there is so that will help in reducing the floods. Okay, floods are like basically the flash floods, okay, due to high pour, okay, high downpour of rain. Okay, and uh, thirdly, we can go for residential cisterns. Okay, so that is tanko reservoir, so they will store water. And one way is one way is to construct wetlands and ponds. Okay, so these are some, this will be some type of artificial aquifers which can store water. Okay, so in terms of transport, in the domain of transportation, we can basically encourage the use of public transit emphasis. Like basically we can use public transport like buses, metros, okay, so local trains, etc. So we can go for pedestrian bicycle friendly. Okay, like we can walk, or we can use forms of transportation which does not use any energy, such as bicycle. And we can build animal bird crossing culverts so that they are not damaged, like they are not harmed. And we can fourthly go for reuse of materials. Okay, so these are some of the ways in transportation how we can address the issue of sustainability. So in case of architectural and building systems, basically we can consider sun, wind, and daylight in our use. We can maximize reuse of structures and materials. We can use natural ventilation. We can consider low flow toilets and urinals. We can consider solar systems to power outdoor lighting, that is parking lots, walkways. So this is happening basically in our IIT also. People like the administration has set up the outdoor lighting using the solar system, so they don't require any electricity from external side. So that is saving the basically also helping in making the institution a cost effective one, and also helping in getting the environmental ratings. And basically it is a one time investment, so our institute is already in that path basically. And we can also use automatic lighting controls that respond to available daylight. Okay, so using some sorts of sensors and all, so all those things can be done. Okay, and one of the main important parameter is keeping ourselves updated, okay, up to date. So in this regard, research and we need to research and learn about new products and technologies. We need to learn from past project experiences. We need to stay up to date through conferences, events, and media. Okay, so these are some of the things which we can adopt uh, at a personal in a personal way. We can also address. Okay, we can work our way. We can add to the cause. Okay, so this way we can address, okay, in a personal capacity basically. So therefore we can also use some tools and incentives. Okay, so there are some useful tools and incentives which are provided for by the government and organizations in this regard. So it is important to implement all those tools and drivers. Okay, so as much as possible, so implementation of tools and drivers. So one is research, government funding, and incentive programs. So these are very highly encouraged nowadays, even in India. And secondly, as you know, our also government is going for net zero emission by 2070 as per the 2021 climate summit. So they're also trying their best to go for net zero emissions. So apart from that, there is utility incentive programs, and also green globes or leadership in energy and environment design credit system, which is basically called as LEED. Okay, so if we go deep into the if we go more about this LEED mission, which is leadership in energy and environmental design. So it is basically, it promotes and accelerates adaptation of green awareness. The mission has been framed to create better buildings and communities, healthy places to live, work, and play. Okay, and various certification levels have been provided in this initiative. So for getting a LEED certification, you need 26 to 30 points. Okay, for getting the LEED certification. For getting LEED silver certification, you need 33 to 38 points. For getting LEED gold certification, you need 39 to 51 points. And for getting LEED platinum certification, so you can get about minimum 52 to up till to a maximum of 70 points. Okay, so 70 is the maximum points that can be provided. So between 52 to 70, you get the LEED platinum certification, which is the best. Okay, so these credits are divided basically in six categories. One is sustainable sites, one is water efficiency, one is energy and atmosphere, one is materials and resources, one is indoor environmental qualities, and one is innovation and design process. So these are some of the categories where we get the credits in the LEED mission. So if you see the percentage of points provided for all the six categories basically. So the innovation and design process gets about 7% roughly of the total points, followed by similarly the water efficiency also gets about 7%. So apart from that, the other four have get a huge share. Like the materials and resources, it accounts for 19% of the total points. The indoor environmental quality, which gets 15 points, it accounts for about 22%. The sustainable sites, which is 14 points, basically accounts for 20%. And the maximum points is awarded for the energy and atmosphere, that is 17 points, and it accounts for 25% of the total rating. Okay, so benefits of these LEED projects are Firstly, it uses less energy and water. Secondly, it uses materials wisely. Thirdly, it produces less waste. Fourthly, it has longer economic lives. Fifthly, it costs less to operate. Sixth, it generates less greenhouse gases and other pollutants. Seven, the occupants are more comfortable. And eight, the occupants are healthier and more productive. So these are some of the benefits of using LEED projects. So these projects basically require architects, mechanical engineers, electrical engineers, structural engineers, transportation engineers, site servicing engineers, and stormwater management engineers. So these are some of the engineers required and architects required for the LEED projects. So uh, so in this regard, we it's very important basically to eliminate the myth that going for green alternatives will cost more. Okay, because everyone is cost savvy. Okay, so people want cost effective solutions. So if there is this myth that going for green or sustainable solutions, it will be very costly. Okay, so people will there will be less encouragement in the society. Okay, so it is very important to eliminate the myth green costs more. Okay, so the steps for staying on track include documentation, which is as early as possible and maintain it. Secondly, update monitor sustainability checklist, that is have a clear picture of progress on sustainable goals. Thirdly, energy or cost models, that is use energy and cost models as design tools. So these are some of the ways. And the budget pointers is basically we should not think about how much more will it cost. Okay, rather we should think how will we do this, how will we achieve the green alternative, or how will we go for the sustainable alternative. So ask early in the project and considered at every step of design and construction. Firstly, how to establish team goals, expectations, and expertise. Secondly, how to include specific goals in the program. Thirdly, align budget with program. And fourthly, stay on track with design and construction. So these are important, and it will take a collaborative effort. Okay, so although we can do a lot of things in individually, but in an individual capacity, but the outputs or the changes will be visible only when it is a collaborative effort. Okay, so everyone joins hands to get to where we need to. Okay, so it will include owners, planners, designers, builders, educators, decision makers, regulators, and they must all find means to work together towards a common goal. Okay, so that is the very important requirement. And basically it has been said by Albert Einstein that the world will not evolve past its current state of crisis by using the same thinking that created the situation. So there's a very beautiful statement given by one of the greatest scientists the world has ever seen. So what you can apply immediately. Okay, so we need to develop a sustainability checklist on projects. We need to recommend sustainable solutions to clients. We need to adhere to sustainability principles in our work, and also we need to use sustainability resources. So we can apply this following criteria immediately. Okay, so we should also it is encouraged to always ponder. Okay, so if not this way, then how? If not now, then when? And if not us, then who? Okay, so these are some of the three questions we should always keep asking. So this so basically the engineering design for sustainability. If we go into the engineering part of sustainability design, so engineers play an important role, okay, in this global sustainable development by designing production systems for materials, minerals, chemicals, energy, electricity generation and distribution, transportation, buildings and other structures, and consumer products. These designs have impacts on the environment, economies, and societies at spatial, that is, at space scales, or that is a 3D scale, that vary from local to global, and at temporal, that is time scales, that vary from minutes to decades. Okay, and as engineers create designs, they not only evaluate their designs at multiple spatial and temporal scales, they also embed their designs in complex systems. Okay, so because basically we take the ideal cases, but basically in reality the systems are not ideal or the simple ones. Those are the complex ones. Okay, so for example from transport sector, field of transportation provides an illustration of the multiple layers of systems in which engineers create designs. Among the most visible products designed by engineers are automobiles. So engineers design engines and improvements to the design of a fossil fuel powered engine for an automobile, which can increase fuel efficiency and reduce the environmental impacts of emissions associated with burning fuels, while simultaneously reducing the cost of operating the vehicle. So this is what is basically engineers work on, and they design in the field of automobile. Okay, so now the size, power and fuel efficiency of the engine must be balanced with the weight of the vehicle. However, so changes in engine design must be considered within the entire vehicle system. Further reductions in emissions and operating costs might be possible by lowering the weight of the vehicle. The use of materials and fuels by automobiles are embedded in complex fuel and material supply systems. So therefore, developing systems to recycle the materials that make up the automobile at the end of its useful life might improve the environmental and economic performance of global material flows. Use of alternative power sources such as biofuels or electricity can impact global flows of fuels, which in turn might impact global flows of materials such as water. Okay. Finally, the design of cities that reduce the need for personal transportation could dramatically reduce the environmental impacts of transportation systems and also transform social structures. So that is the capacity. Okay, so basically, if you see, this is the engineering design for sustainability. It can consider a variety of system scales. As for example, the automobile subsystem, which is engine paint. Okay, the automobile, which has three components: manufacture, use, recycle, and infrastructure technology system. So it can be build infrastructure, example highways, or supply infrastructure, example petroleum industry. The social structure system can be in the form of example of dispersed communities and businesses or malls. Okay, so and basically engineering design for sustainability can consider a variety of system skills as shown for the automobile. So it can be gate to gate, okay, which is subsystem; cradle to grave, okay, that is the automobile; inter-industry infrastructure; and extra industry societal. Okay, so it can be of various types. So the point of this example is to illustrate that sustainable design of engineered systems will lead to consideration of multiple spatial and temporal scales, and will require that the engineer interact with professionals with many different backgrounds both within and outside of engineering. These sustainable design challenges are complex, and the tools for addressing these problems are still emerging. This lecture will introduce the tools that are currently available, which are a combination of principles and quantitative analysis methods. So we'll be basically trying to understand them. Next, because sustainable designs must be able to compete in the marketplace, quantitative methods for evaluating and in some cases monetizing environmental externalities will be discussed, and the use of other non-monetized environmental indicators for evaluating process technologies and product alternatives will also be described. Indicators of social impact for engineering design are only at the initial stage of development, yet some prototype methods have been proposed and used, and an introduction to this emerging area will be presented. So we will be coming in the forward slides. We will be discussing about all of this and go understand fully understand the sustainable engineering design principles. So as we all know, the sustainability term has been coined by the Brundtland report. Okay, so achieving our needs without hampering, jeopardizing the needs of the future generations. Okay, it is basically there was some of the principles were coined in Hanover. So that is a place in Germany. So in some summit in Hanover, so one principle was coined, that is human systems must be designed to coexist with natural systems. So this principle was accepted by all in Hanover. And also there was a Augsburg material declaration. So this place is also in Germany. So in 2002 there is Augsburg materials declaration, where it was decided to integrate integration of environmentally benign design, that is environmentally friendly design, materials and manufacturing over all stages of the life cycle, optimization and exploitation of raw materials and natural resources, energy efficient production technology and product distribution, regenerative energy sources, durability, recyclability, and closed loops. So these are some of the concepts decided in the Augsburg Materials Declaration. And also one summit was held in Sandestin. Okay, so that is a golf and beach resort in Florida. So there also sustainable engineering principles were framed in Sandestin. So one was engineer processes and products holistically, use system analysis and integrate environmental impact assessment tools. Secondly, conserve and improve natural ecosystems while protecting human health and well-being. Thirdly, use life cycle thinking in all engineering activities. Fourthly, ensure that all material and energy inputs and outputs are as inherently safe and benign, that is friendly, as possible. Fifthly, minimize depletion of natural resources. Sixthly, strive to prevent waste. Seventh, develop and apply engineering solutions while being cognizant or aware of local geography, aspirations, and cultures. Eighth, create engineering solutions beyond current or dominant technologies. Improve, innovate, and invent technologies to achieve sustainability. Ninth, actively engage communities and stakeholders in development of engineering solutions. So these were some of the main mottos, okay, as per the Sandestein, the sustainability summit, okay, the people had agreed upon. And from that also, all of these summits, the principles of green engineering were coined, okay. So here are some of the main principles are basically 12, okay. So 12 principles of green engineering were coined. So let us one by one see all the principles. So the first principle is designers need to strive to ensure that all material and energy inputs and outputs are as inherently non-hazardous as possible. Second principle, it is better to prevent waste than to treat or clean up waste after it is formed, okay. So basically prevention is always better than cure, okay. Third principle, separation and purification operations should be designed to minimize energy consumption and materials use. Fourth, products, processes, and systems should be designed to maximize mass, energy, space, and time efficiency. Fifth, products, processes, and systems should be output pulled, okay, rather than input pushed through the use of energy and materials. So basically, the performance should be the main criteria. Like we should have the output which is green, okay, which is green positive, okay. So rather than trying to push inwards, from the inside, instead of pushing, we should try to pull it from from the outside, okay, from the output way, so that it is a green positive output. Okay. The sixth principle is embedded entropy and complexity must be viewed as an investment when making design choices on recycle, reuse, or beneficial disposition. Seventh principle, targeted durability, not immortality, should be a design goal. Okay, so we should go for durability instead of making it immortal. Okay, so that is not possible in reality. So why waste time or use resources which is not required? Okay, so we should always go for durability. And eighth principle, design for unnecessary capacity or capability, that is one size fits all concept, okay. So those solutions should be considered a design flaw, because you are again using unnecessary capacity, so that is again destroying the resources, okay. Ninth principle is material diversity in multi-component products should be minimized to promote disassembly and value retention. 10 principle, design of products, processes, and systems must include integration and interconnectivity with available energy and materials flows. 11 principle, products, processes, and systems should be designed for performance in a commercial afterlife. And 12th principle, material and energy inputs should be renewable rather than depleting. Okay, so these are the 12 important principles of green engineering. Okay, so these engineering design principles establish a framework for designing more sustainable products and and processes. At first, changes in engineering design are likely to be improvements to inherently unsustainable products and systems, but over time it is hoped that these design principles will move industry and consumers toward inherently sustainable products and production systems. However, there will be tensions in applying these principles. What if making a process inherently safer requires more energy? What if minimizing water use requires more energy? Engineers are accustomed to addressing trade-offs between objectives, but methods for doing so require measures of performance. In most engineering designs, the measure is the cost, because it should be cost effective. Ultimately, what will sell in the market is cost effective solutions. Okay. In delivering a specified level of performance of a product, technology, or service, the goal is to minimize cost. This suggests that one mechanism for incorporating objectives related to sustainability into engineering design is to monetize them. Okay, so this is one of the way. And basically, uh, through the creation of economic performance indicators. Okay, so the cost associated with poor environmental and societal performance can be very large. The waste disposal fees, permitting costs, and liability costs can all be substantial. Wasted raw material, wasted energy, and reduced manufacturing throughput are also consequences of waste and emissions. Corporate image and relationships with workers and communities can suffer if performance is substandard. But how can this cost be quantified? Okay, so that is one important parameter. Okay, one important question. So tools available for estimating environmental and societal costs and benefits. So let us see. So this include traditional concepts, okay, such as the time value of money, present value, payback period, internal rate of return, and other financial evaluation calculations. Non-traditional tools include methods for monetizing environmental costs that are hidden from normal accounting procedures, less tangible costs and benefits that can still be monetized. So these are some of the tools we can take. Okay, in general, traditional accounting practices have acted as a barrier to implementation of sustainable engineering projects because they hide the cost of poor environmental and societal performance. Many organizations are now giving more consideration to all significant sources of environmental and societal costs. The principle is that if costs are properly accounted for, management practices that foster or bring about good economic and societal performance will also foster superior environmental and societal performance. Okay, so if the management practices provide good economic and societal performance, it will also provide superior environmental and societal performance. Okay, so it is vice versa. Okay, in this concept there are some accounting terms, environmental accounting terms we need to find the definition of. Okay, so one is internal costs. These are some of the terminologies associated with environmental accounting terms. One is internal costs or private costs. So they are the costs that are borne by a facility. For example, cost for materials and labor are examples of internal costs. Okay, second is the external costs or societal costs. So these, on the other hand, are the cost to society of the facility's activities. The cost associated with the loss of fishable waters due to pollutants discharged by a facility to a stream is an example of an external cost. Okay. Often environmental fees, regulations, and requirements act to internalize what would have otherwise been an external cost, so that a facility that produces waste must pay to reduce its quantity or toxicity or pay a premium for its disposal. So that is an idealized scenario. A typical management accounting system for a manufacturer would include categories for direct materials and labor, costs that are clearly and exclusively associated with a product or service, manufacturing overhead, sales, general and administrative overhead. Overhead was basically the operating cost, okay, and research and development. Environmental and societal expenses can be hidden in any or all of these categories, but are charged most often as overhead. That is the operational cost. Often, even the direct environmental costs that could be assigned to a particular process, product, or activity, such as waste disposal, are lumped together facility wide. This is often done because of practices such as using a single waste disposal company to manage all of a facility's waste. Other environmental costs, such as the cost of filling out forms for reporting waste management practices, are also hidden in the overhead category. Because environmental and societal costs are not traditionally allocated to the activity that is generating waste, some of the benefits of green engineering projects are masked because we don't take into account the societal and environmental costs, okay, in the traditional system. It is not allocated to the activity which is generating waste. That's why green engineering projects are basically, the benefits are basically reduced. It is masked. It is not visible. Full cost accounting is a type of managerial accounting in which as many costs as possible are allocated to products, product lines, processes, services, or activities. Even though full cost accounting does not focus particularly on environmental and societal costs, it promotes improved performance because the costs of producing waste and societal impacts for individual processes or products are revealed, providing management with a better idea of true costs. Activity based costing is similar to full cost accounting, except that the costs are allocated to specific measures of activity. And for example, in activity based costing, the cost of generating a particular kind of waste per pound of production might be measured. Okay, so it is basically activity based costing is similar to full cost costing only, except the costs are allocated to specific measures of activity, okay, not the total. Okay, so basically it can be a particular kind of waste per pound, okay, of production, it can be measured, okay, the cost. Estimates of environmental costs. Not all environmental costs are captured in traditional accounting and capital budgeting practices. Nevertheless, some measures of environmental and societal costs are available, providing a rough indication of the magnitude of costs and the variation of those costs among industry sectors. Among the easiest environmental costs to track are the costs associated with treating emissions and disposing of waste. So, this basically these expenditures are not distributed uniformly among industry sectors. If you see the next slide, this is the one. So the sectors such as petroleum refining and chemical manufacturing spend much higher fractions of their net sales. So petroleum and chemical manufacturing, okay, so this one, so they basically spend a much high, okay, much high percentage and much higher fractions of their net sales and capital expenditures on pollution abatement, okay, like how to reduce it, how to tackle it, then do other industrial sectors. So it is visible, it is clearly visible here if you see. And therefore in these industrial sectors, minimizing cost by preventing waste and emissions will be far more strategic an issue than in other sectors, because they basically spend much high fraction, okay. So if you can manage the like if you try to prevent the waste and emissions directly, the amount of money spent on the basically on pollution abatement will be directly reduced, and that will definitely increase their shares of income or turnover, okay. So if you see here, this is the data of pollution abatement expenditures by US manufacturing industries. So this is the percentage in pollution control expenditures as percent of sales. This is pollution control expenditures as percentage of value added, and this is pollution control capital expenditures as percent of total capital expenditures. So if you see here, petroleum has the maximum, okay, and chemical also has a very high number, okay, 13.4. Rest are like relatively if you see the down values, it is very less. So if you can directly control the pollution, you are directly uh, reducing the cost, okay. So you are that is basically increasing the profit of that company, okay, or that sector, okay. So this is a data as per the US Congress Office of Technology Assessment 1994. So this is basically a problem. Let us see this problem and its solution. So pollution control costs, okay, related to potential pollution control costs for GHG, greenhouse gas. So the problem is estimate the control cost for greenhouse gases for an electricity generating unit, EGU, okay, or power plant as a percentage of sales revenues. So for that, assume that the EGU, that is electricity generating unit, uses coal as a fuel and converts the heat of combustion of coal into electricity with 35% efficiency. Secondly, the heating value of coal is 10,000 BTU, that is British thermal units per pound. Thirdly, coal is 85% carbon. Assume that. Fourthly, carbon costs $20 per ton to capture and sequester. And fifthly, electricity can be sold for $0.10 per kilowatt hour. Okay, so these are some of the assumptions we need to take in the problem. So let us see the solution. So for like for per ton of carbon, what is the electricity generated? If you want to find that, so we just need to convert, okay. So 1 ton of coal basically, so like basically 1 ton of coal, it will require around 80, it basically will contain 85% carbon, that is 0.85 ton carbon, okay. So 1 ton of coal is equivalent to 0.85 carbon. So if you like basically want to convert this, okay, into pound, okay, pound per ton, okay. So 1 ton is basically 2000 pounds, okay. So we multiply this, so we are basically trying to convert this this ton of coal into kilowatt hour, okay. So that is the energy, okay. So total energy basically. power, basically power in terms of electricity, okay, generated. So for that we are basically converting like ton to pound. So 1 ton is 2000 pound, and then the pound we want to convert into BTU, that is British thermal units. So 1 pound of coal is equivalent to 10,000 British thermal units. And like basically converting again converting BTU into kilowatt hour. So 1 kilowatt hour is equivalent to 3412 British thermal units. Okay, so these are some standard values. And because the electricity is generated, the efficiency of that is 35%, so you need to multiply by 0.35. Okay, so performing the calculation, we get the value as 2415 kilowatt hour per ton carbon. Okay, so per 1 ton of carbon it will generate 2415 kilowatt hour power, that is in terms of electricity. And it has been given in the question, this one, that the control costs are $20 per 2415 kilowatt hour of generation. Okay, so we need to find the control cost for greenhouse gas as a percentage of sales. Okay, sales revenue. So if uh, per kilowatt hour, so why we're converting from 1 ton to kilowatt hour? Because the electricity sold is $0.10 per kilowatt hour. So the money generated per the money generated is shown in terms of kilowatt hour. Okay, so if it would have been in terms of ton only, we did not have to convert. Okay, so because it is in amount generated, the money generated is in terms of kilowatt hour, so that's why we needed to convert. So 1 kilowatt hour generated $0.10. Okay, so therefore 2415 kilowatt hour will generate how much? It will generate 241, roughly $241. Okay, so if you divide, our question is find the control cost as a percentage of sales revenues. Okay, so we basically need to divide this 20, which is the control cost, $20 per ton. Okay, so we have been everything is in per ton. Okay, per ton. So per ton, if basically per ton, per ton of carbon. Okay, so if $20 is the cost, control cost, and the sales is $241, so dividing this by this 20 by 241 and multiplying by 100, we get the percentage. Okay, so if you do that, 20 by 241 into 100, you get 8%. Okay, so this much generation leads to $241 in electricity sales, so the control costs are about 8% of sales. So the answer is 8%. Okay. So this is a table which shows a summary of environmental costs at the Amoco Yorktown refinery. So these are some of the cost categories such as waste treatment, maintenance, product requirements, depreciation, administration, compliance, sulfur recovery, waste disposal, fees, fines, penalties, and this is a total cost. And here is the percentage of annual non-crude operating costs. The percentages are provided, and this is, I think, the total. Okay, so total cost is 21.9%. Okay, so many costs are there, like all may not have been provided. So total adding, we get the total cost is 21.9%. And this source has been taken from Heller. Okay, study conducted by Heller in 1995. So the third table is basically summary of environmental costs at the DuPont Laporte chemical manufacturing facility. This is a facility in USA. So similarly, they have found the total as 19.1%, the percentage of manufacturing costs using all. So this is the environmental costs, okay, at the Laporte DuPont chemical manufacturing facility. So a framework for evaluating environmental costs is basically required. So engineering projects are generally not undertaken unless they are financially justifiable, and projects designed to improve environmental and societal performance beyond regulatory requirements usually must compete financially with all other projects under consideration at a facility. Fortunately, projects resulting in improved environmental and societal performance are frequently profitable. However, the potential profitability of environmental and societal projects is difficult to assess, and it is common for many of the financial benefits of improved environmental and societal performance to be neglected when projects are analyzed. That is why a better understanding of methods for estimating these costs and benefits serves to promote sustainable engineering. Okay, so How to find a total cost assessment methodology? So basically, there are five tiers in that. Okay, so first tier is cost normally captured by engineering economic evaluations. Second tier is the administrative and regulatory environmental costs not normally assigned to individual projects. Third tier is the liability costs. Fourth tier is costs and benefits, so internal to a company associated with improved environmental and societal performance. Fifth tier is costs and benefits external to a company associated with improved environmental and societal performance. So this has been developed by American Institute of Chemical Engineers Center for Waste Reduction Technologies, that is AICHA CWRT, in 2000. So, in financial analysis, cost traditionally evaluated the following. Okay, one is the capital equipment, one is materials, one is labor, one is supplies, one is utilities, one is structures, and one is salvage value or recovery value. So, the environmental costs often charged to overhead. Okay, so what are the various environmental costs often charged to overhead to operation? Okay, the charges for operational related costs. Okay, so the various costs, okay, environmental costs often charged are: one is offsite waste management charges, one is waste treatment equipment, one is waste treatment operating expenses, filing for permits, taking samples, filling out sample reporting forms, conducting waste and emission inventories, filling out hazardous waste manifests, is inspecting hazardous waste storage areas and keeping logs, making and updating emergency response plans, sampling stormwater, making chemical usage reports, reporting on pollution prevention plans and activities. So these are some of the environmental costs often charged for overhead or operation. The liability costs could include basically the compliance obligations, the remediation or ways for the obligations related to stopping of environmental damage, that is basically remediation, fines and penalties, obligations to compensate private parties for personal injury, property damage, and economic loss, punitive damages, and natural resource damages. So this is the environmental performance indicators. These are some of the examples. So if you see here, the basic system, okay, so that is raw material extraction, then material processing, product manufacturing, and use, reuse, disposal. This is a system boundary basically. So from that, the waste are coming, pollution control. So these are basically the life cycle stages. So from that, as per the impact assessment, so there is midpoint and end point. Okay, so midpoints basically can result as can be in the form of global warming, ozone depletion, smog formation, acidification, and ecological harm. And endpoints will basically, endpoint will basically be human health and ecosystem damage. Okay, so there is an example of an environmental performance indicator, a generic product life cycle showing key stages in a product system, key inputs and waste, effects of emitted waste on midpoint damages in the environment, and endpoint damage to humans and ecosystems. So it is an flow chart basically. So if you see here, it is the environmental mechanisms involved in conversion of emissions of CFCs, that is chlorofluorocarbons and halogens. Okay, so basically elements which belong to the halogen family. Okay, so into midpoint and endpoint damages. Okay, so halogen is basically those elements which required one electron to form an octet. Okay, so they have seven. So yeah, so that's why they are very reactive, and also they are very hazardous for people. Okay, so hazardous, they result in hazardous, they are basically toxic. Okay, so there's hazardous for people if they come in direct contact. So examples of emissions of CFCs and halogens into midpoint and endpoint damages as per uh, as adapted from Bayer. Okay, research done by Bayer in 2003. So if you see here, this is the emission event, chlorofluorocarbon, CFC, emissions from processes or end use. So the next step is the stage is the environmental transport or transformation. So basically transport to stratosphere, release chlorine, ozone destruction, etc., and that result in the next stage of midpoint damage indicator, which is ozone loss in stratosphere, ozone depletion potential, which is ODP, and finally we get the last stage, which is the endpoint damage. Okay, so increased UVB radiation leads to the following damages. So UVB is basically the shorter wavelength of ultraviolet radiation. So because wavelength is short, the frequency will be very high. So energy is, we all know, it is E equal to h nu. so the energy will be very high, so it can cause sunburn. Okay, and apart from that, the various damages can it can occur extreme. If it is the exposure is extreme, it can lead to skin cancer, crop damage, immune system suppression, damage to materials, marine life damage, cataracts. Okay, so this is environmental cause and effect chain. Okay, so the life cycle impact assessment here, this part is very important. Okay, the emissions and waste from a product life cycle constitute the inventory upon which environmental impact indicators are based. Life cycle inventories do not by themselves characterize the environmental performance of a product, process, or service. This is because overall quantities of waste and emissions as well as raw material and energy requirements must be considered in conjunction with their potential effect on the environment. Simply stated, a pound of lead, okay, lead emitted to the atmosphere has a different environmental impact from a pound of iron emitted to surface waters. To develop an overall characterization of the environmental performance of a product or process throughout its life cycle, it requires that life cycle inventory data be converted into estimates of environmental impact. Okay, so that is the important part. Okay, so it should be the inventory data must be converted into estimates of environmental impact. So with this, we come to the end of the 7-week lecture. Okay, so now let us try to further understand the lecture basically by solving a few problems based on it. The first question is basically why reduce is the most preferred option out of 3 R's. Okay, so reduce, reuse, and recycle. So out of that, why reduce is the most preferred option? Firstly, A, it will help in reducing the energy consumption in manufacturing the product at the very first stage. B, it will help in reducing the raw material consumption involved in manufacturing the product at the very first stage. Third, C, it will help in designing material with better recyclability. D, none of the above. So out of A, B, C, and D, which is the correct option, or which are the correct options? So if you see here, A, it will help in reducing the energy consumption in manufacturing the product at the very first stage. So this is true. If it is there is reduction, so the energy consumption will also reduce. Okay, during manufacturing. So A is correct. B, it will help in reducing the raw material consumption involved in manufacturing the product at the very first stage. So this is also true. If it is reduced, the consumption is reduced, so the raw material consumption will also get reduced during manufacture. So B is also correct. C, it will help in designing material with better. So this is not correct. Okay, so this may like the reduction does not lead to recyclability. Okay, so there is no interrelation. So C is not like not the correct. C is not correct. Okay, so there is no this one no relation between reducing and recycling. So therefore A and B are the correct options. So if you see A, it will help in reducing the energy consumption in manufacturing the product at the very first stage, and B, it will help in reducing the raw material consumption involved in manufacturing the product at the very first stage. So these two are the correct options. Second question, what are the three pillars of sustainability? A, environment, economy, social aspect. B, profit, preservation, production. C, production, people, profit. Or D, ecology, social aspect, preservation. So out of A, B, C, and D, which is the correct option? Okay. So if you remember the three pillars, so basically they are the environment, economy, and social aspect. So in the traditional economy, the economy was the main part, followed by environment, and last was the social aspect. But after this advent of sustainability, all the three were basically interrelated or interconnected, or there was intersection. Okay, so uh, like basically we consider sustainability has its meaning in three pillars. Okay, three forms, that is environment, economy, and social aspect. So A is the correct option. So as you can see, A, environment, economy, and social aspect is the correct option. Third question, changes need to be made to move from traditional engineering to sustainable engineering? A, maximize the utility of the product without considering the cost. B, maximizing the social benefit at the cost of ecology. C, maximizing the social benefits while minimizing the ecological impact. D, maximizing the use of natural resources without considering the cost. Okay, so A, B, C, and D, which is the correct option? Okay, so basically, if you remember traditional engineering, it was basically maximizing the utility and minimizing the cost of client. Okay, so that was traditional. And sustainable engineering, basically it was maximizing the social benefit and minimizing the ecological impact. So if you see here, yeah, so C is the correct option. Okay, maximizing the social benefits while minimizing the ecological impact. So C is the correct option. So if you see C, maximizing the social benefits while minimizing the ecological impact is the correct option. Fourth question: which of the following is leading towards sustainable development? A. Use of renewable energy sources. B. Designing products with low energy requirements. C. Designing product with low material consumption. Or D. All of the above. So out of A, B, C, and D, which is the correct option? So if you have like properly understood the sustainable development concept, so basically all the three are important. So it for this to happen, we need to use renewable energy resources sources. Second, we have to design products with low energy requirements, and third, design product with low material consumption. Okay, so that is basically maximizing social benefit with minimizing ecological impact. So all the three are important. So basically D, all of the above, is the this one correct option. Okay, so if you see D, all of the above, is the correct option. Fifth question: which of the following is a sustainable approach for rainwater harvesting? Okay, so is it A. Collecting rainwater in an open pond with shallow depth and large area? B. Is it diverting rainwater into underground storage tanks with proper filtration systems? C. Is it disposing of rainwater into the sewage system? Or D. All of the above? Okay, so out of A, B, C, and D, which is the sustainable approach for rainwater harvesting? Okay, so disposing of rainwater into the sewage system can never be a sustainable approach. So C is not correct. So because C is not correct, all of the above also is not correct. So C and D both are not correct. Collecting rainwater in an open pond with shallow depth and large area, so that is not a sustainable approach. Okay, basically that is basically a normal approach. Okay, sustainable is basically this one, like how if we can convert rainwater into underground storage tanks, okay, with proper filtration system. So how to convert that rainwater, okay, and divert it to transfer it to underground storage tanks with proper filtration system. So B, diverting rainwater into underground storage tanks with proper filtration system is the correct approach, sustainable approach. Okay, so B, as you see, B, diverting rainwater into underground storage tanks with proper filtration system is the correct sustainable approach. Okay. 6. Which of the following indicates endpoint damage? A. Skin cancer. B. Crop damage. C. Marine life damage. Or D. All of the above. So out of A, B, C, and D, which is the which of the following indicates the endpoint damage? So if you remember this slide, so endpoint damage. So one is skin cancer. So this is A, is correct. B was crop damage. So if you see, crop damage is also there. So B is also correct. C, marine life damage. So marine life damage is also there. So C is also correct. So that means all the three are correct. That is D, all of the above. Okay. So D, all of the above is the correct option. So as you can see, all of the above is the correct option. D. Seventh question: which of the following is a principle of green engineering? A. Embedded entropy and complexity can be ignored when making design choices on recycle, reuse, or beneficial disposition. B. Targeted durability, not immortality, should be a design goal. C. Material and energy inputs and outputs should be maximized. D. None of this. So out of A, B, C, and D, which is the correct option? So if you remember the principles which we have just discussed of green engineering, so this embedded entropy and complexity has to be taken into account. Okay, so it can't be ignored. Okay, while making design choices on recycle, reuse, or beneficial disposition. Okay, so that's why, because in nature everything is complex. Okay, and the hidden entropy or energies therefore has to be taken into account. So A is incorrect. Okay, if you see B, targeted durability, not immortality, should be a design goal. So this is correct. Okay, so we should always go for durability, not immortality, because that will lead to unnecessary wastage of resources. So B is correct. C, material and energy inputs and outputs should be maximized. So output should be maximized, but input should be minimized. Okay, that is the green engineering concept. So both should not be maximized. So C is also incorrect, and because B is correct, so D, none of this is also not correct. Okay, so correct answer is B, targeted durability, not immortality, should be a design goal. As you can see, B, targeted durability, not immortality, should be a design goal, is the correct option. question: which of the following is not a midpoint indicator among the environmental performance indicators? A. Acid rain. B. Human health damage. C. Ozone depletion. Or D. Global warming. So out of A, B, C, and D, which is not a basically midpoint indicator? Okay. So if you remember that slide, so if you see here, acid rain, so that is a acidification. Okay, so that is a midpoint indicator. Okay, in the environmental performance indicator, so is acidification is a midpoint indicator, so this is not correct. It is not correct. Human health damage, so yeah, so this is endpoint. Okay, so that is not midpoint, so B is correct. Okay, so it is not a midpoint indicator, B is correct. The ozone depletion, yeah, so this is a midpoint, so it is not a, it is a midpoint indicator, so C is not correct. And the global warming, so it is also a midpoint indicator, so D is also not correct. So what is correct? It is B, human health damage. So human health damage is not a is not a midpoint indicator as per the environmental performance indicator. So as you see, B, human health damage is the correct option. Ninth question: assume that from 1 ton of coal, 2000 kilowatt hour of electricity can be generated, and electricity cost is 120 paise per kilowatt hour. If the cost of carbon capture and sequester, that is control cost, for 1 ton of coal is rupees 400, control cost represents how much percentage of the electricity sale generated from 1 ton of coal? Is it A 16.67%? Is it B 9.67%? Is it C 12.25%? Or is it D 10.33%? So out of A, B, C, and D, which is the correct option? So this question is similar to the one which we solved in the lecture itself, right? So let us see the solution. So here if you see, the electricity cell generated for 1 ton of coal, it is basically 120 paise per kilowatt hour. Okay, and so therefore there is in like for per kilowatt hour is 120 paise and electricity cost, and 1 ton of coal, it basically requires 2000, like from 1 ton of coal basically 2000 kilowatt of electricity can be generated. So what will be the electricity cost? It will be 120 into 2000, right? In terms of paise, so it is 2,40,000 paise, which converted to rupees is 2400, right? And what is the control cost given for 1 ton of coal? It is rupees 400. So control cost for 1 ton of coal is rupees 400. Therefore, what is the percentage of electricity sale represented by control cost? It is 400 by 2400 into 100, right? So solving, we get 16.67% is the answer. So that is A. Okay, 16.67% is the correct option. If you see, A, 16.67% is the correct option. 10th question: which of the following is or are example of internal environmental costs? A. Cost associated with loss of agricultural land due to waste disposal. B. Cost of material. C. Cost associated with labors. Or D. Societal cost. So out of A, B, C, and D, which is the correct option? So if you remember the environmental accounting terms, so internal costs basically are private costs, that are basically the costs that are borne by a facility. So cost for materials and labor are examples of internal costs. So cost of materials and labors. Okay, so B and C are correct. Okay, and if you see external costs or societal costs, so they are basically on the other hand are the cost to society of the facilities activities. Okay, so this is societal cost. Okay, so that is not internal. Okay, and the cost associated with the loss of fishable waters due to pollutants discharged by a facility to a stream is an example of an external cost. So similarly, loss of agricultural land due to waste disposal can also basically, instead of the fishable water, if you replace that with agricultural land due to waste disposal or due to pollutants, so that is basically cost associated so with the external cost. Okay, so therefore, which is the example of internal environmental cost? It is cost associated with materials and labor. So B and C are the correct option. So if you see here, the correct option is B, cost of material, and C, cost associated with labors. So these two are the correct options. So with this, we come to the end of today's problem discussing session. So let us meet next Sunday for the 8th lecture. So with this, I would like to end today's discussion. Good night.